So I think it's 9, so we can begin the colloquium. So welcome to the Collège de France for this one-day colloquium about Holocene North African climate. And this is the program is listed on the slide that you see here. So I organized this together with my colleague and friend Peter Domenical, who is right next to me here, from Columbia University. And so the program for today is listed. So I mean, with different speakers from different universities. We will hear Stefan Kröpelin from the University of Cologne, Florence Sylvestre from Aix-en-Provence, from the CEREGE, Jessica Tierney from Woods Hole Oceanographic in the USA. Then after the lunch break, we will have Peter Domenical, Yannick Garcin from the University of Potsdam, Martin Clausen from the Max Planck Institute of Meteorology in Hamburg. And after the coffee break in the afternoon, we will hear more about man and ancient societies and modern societies in Africa with Laura Botiguet from Stony Brook in the US, and Paul Sereno from the University of Chicago about the Gobrero complex. And we will have a roundtable discussion about the whole thing. And at the same time, the workshop is meant as being quite flexible, and there will be at the same time review information and some original data that, because we are all actively working in this topic, and so there will be, I hope, some fruitful exchanges also during the questions. The first thing that we wanted to do with Peter and colleagues is to dedicate, in fact, this workshop to our colleague and friend Françoise Gass, who passed away only, less than a month ago. She was a pioneer in the field of Paléoclimatology and the research especially in North Africa. She was really a pioneer of the field, of the very topic that we are discussing today. And so we were shocked and very sad, extremely sad when we knew about this death. So we would like to dedicate, in fact, this workshop to her memory. And these are two pictures of Françoise, a very common one with Françoise at her microscope. In fact, she was a specialist of diatoms, of lacustrine diatoms, and so she spent most of her career in studying diatoms to reconstruct the pH and the salinity of ancient lakes. And for this, she received many awards, and here you have a picture of the King of Sweden with Françoise awarding, in fact, to Françoise. She was the first female recipient of the Vega Medal of the Swedish Society for Anthropology and Geography in 2005. She also received, for example, the Hans Oeschger Medal of the EGU, which is a highly recognition. But first of all, what Françoise is very known for is for many seminal contributions on North African paleoclimates. These are a few key papers that, in the title of a few key papers that she published over the last decades. In fact, she started, for example, with studying, in fact, the Lake Abe in Ethiopia. I will come back to this lake, the evolution of the history of the lake level, Lake Abe. This is published in 1977. At that time, she was affiliated to the Laboratoire de Géologie du Quaternaire in Meudon-Bellevue, so close to Paris. And then she moved to Orsay to team up with geochemists, especially Jean-Charles Font. And she did most of her career there. This is a paper that she did. She conducted on the water level fluctuations of Lake Tanganyika. You have also another major article about the very topic that we are discussing today, the arid-humid transition in the Sahara, with, in that case, two sites, one close to the Lake Chad, that we will also talk about today, and Algeria, the Great of Algeria. And more recently, something like 15 years ago, in fact, she moved to Aix-en-Provence, to the CEREGE, where our institution, with Florence Silvels and myself and other colleagues. And she has been very active also in the field. She went on in many parts of the world, North Africa, but also in the Near East, in Lebanon. Recently, she was in the field. She worked also in Madagascar, in Tibet, and so forth. And this is one of the key review papers that was published in 2000 while she was at CEREGE. And she did many contributions to the field. So this was more or less meant as an introduction that we wanted to show with Peter. So now I will begin, in fact, what I intended to show you as a... You want to add something, Peter? What I wanted to show you as an introduction to the workshop, at the same time, doing a review on the whole topic would take, a full lecture series. And what I did is by no means a comprehensive review, but these are only a few information that are quite important, I think, and will be discussed today, and there will be no conclusions because the whole thing will be open for the discussion of today. So, again, I will start by showing to you these 2 pages extracted from the review paper by Françoise Gasse in 2000, in which she was showing many sites. In fact, she made an attempt, in fact, to review the information about ancient lakes during the glacial time periods and the more recent periods in Africa as a whole. And you have the map with different sites, and that some of them will be discussed today again. And this is a photograph that Françoise sent to me some time ago when I was teaching on the subject. This is a picture of the Lake Abbé deposits. Some of them are hundreds of meters above the present altitude of the lake. So this is still in black and white, but a similar picture of so Lake Abbé is right here in Ethiopia, in the northern part of Ethiopia, close to Djibouti, actually. And this is another lake. This is also quite famous, and she worked also on the Lake Assal. This is a picture of the Lake Assal with the Holocene deposits that are white, that are directly on volcanic rocks. So it is quite stunning to see this. Close to Djibouti, and you see the remaining lake in the back. And in that paper, Françoise was reviewing and comparing, in fact, the information that were available at that time on the time evolution. This is what is represented on that panel page of the time evolution of the lake level for these different lakes, starting from the Lake Abbé that she began to work in the 70s, Lake Turkana, Lake Albert, Lake Tanganyika that she worked on, and Lake Malawi. So different authors were also involved in this work. And this is the time scale. I mean, here, what is represented is the height above the present level of the lake. You can see that, for example, the Lake Abbé was 200 meters above the present level sometime in the distant past, so in that case, 30,000 years before the present. Here you have the time scale that is evolving from right to left. The 0 is the modern time period for those who are not used, in fact, to this kind of graphic. And the time evolution is going from right to left. And you have the time evolution of these lake level, and with high levels up to 200 meters for Lake Abbé in that case. And she made an attempt, in fact, to compare and to synthesize, in fact, all the information that was coming from these lakes that are either fossil, I mean, paleo lakes, or are still existing, but at different levels in the past. When we zoom and we take a close-up on what Françoise did as a review, for the Holocene. The Holocene is the time period that corresponds to more or less the last 10,000 years in carbon-14 ages. So this is, you have again a time scale here. This is taken from the original review paper, I mean, with covers. this is a slide that François shared a while ago. This is starting at 10,000 years in C14 ages. This 1 kiloyear is again 1 millennium. And the 0 is the modern time period. You have again the lacustrine fluctuation during the Holocene of the Lake Abbé. You have also another complex, Bar El Ghazal, Bosuntwi. So what she was attempting, in fact, to synthesize was the different information to compare the dating of these levels and to identify a lacustrine optimum high lake level at the beginning of the Holocene that is very clear on that graph. And this is more or less what we will study today, the African humid period that is corresponding to those high lake stands. And at the same time, she was reviewing also the information on more complex structures, fluctuations of the level of the lake, and with dry periods that were sometimes corresponding between the different systems, especially one that is corresponding to 7,000 to 8,000 years in carbon-14 ages, and also she provided a few correspondence with the actual calendar ages, and I will come back to that, the importance of using calendar ages for this proper work. When we compare, for example, with astronomy, it's very important to have accurate, not only precise carbon-14 ages, but also true ages. So this is more or less, this dry phase, this drop of the lake is corresponding to a phase that is dated around 8.2 thousand years. And we will come back to that. And other, she identified, in fact, other time periods of fluctuations as well. So during this time period of the early Holocene, with this humid period identified in lakes, there were also major changes that happened somewhat north in the Mediterranean. And we know that, in fact, from the study of deep sea sediments, and especially at the beginning, this African humid period more or less corresponds, in fact, to the timing. We can discuss about it later, but the timing of the deposition of an organic rich layer in the eastern part of the Mediterranean and also in the western part, which is called the sapropel. So this is the sapropel 1, the first one appearing in the stratigraphy. That occurred about between 10 to 6K in that case calendar years. And the thinking, there is an entire literature about these sapropels, but the thinking is, after the work of the pioneering work of Martin Rossignol-Strick, is linked to the fact that the hydrology, due to this higher precipitation, higher pluviometry during that time period, and also higher input of rivers, we will see the case of the Nile River that is very important for that time period. The eastern Mediterranean, that is today functioning with an anti-estuarine circulation, was stratified, and due to this stratification with freshwater input from rain and from the rivers that are indicated here by the big arrows, especially the Nile River. And because of this stratification, there was input of more upwelling of nutriments at the surface, but at the same time also suboxia or even anoxia in deep sea sediments that allowed, in fact, the deposition of laminated organic rich sediments, the sapropels. So just to illustrate with a very recent work that was published it's not even published, it's a preprint. This is from a work by the Dutch team of Utrecht, by Enneka Medal, who studied very precisely at high resolution, in fact, the time period corresponding to this early Holocene. This is a high resolution record of a core that is located off the Nile Delta. And this is a summary graph of the study with a few proxies, paleoclimatic proxies that can be used, in fact, to study the fluctuation of the Nile input and at the same time the stratification and the sapropel deposition. The sapropel deposition, you can see that directly with the percentage of organic carbon that is represented here. So the phase is starting at 10,000 years before present and is ending at 6.5 thousand years before the present. And at the same time, there are other proxies that can be used, in fact, to study the stratification, I mean, the salinity and the input of the rivers that are the titanium to aluminum ratio, and also the delta weighting, the oxygen isotopes in foraminiferous at the surface. And we can see that the freshening at that site, at least, began, in fact, much earlier than the deposition of the sapropel. It began at around 12, 11.5. That is actually corresponding, in fact, to the beginning of the Holocene in real calendar years. So more or less corresponding to 10,000 in carbon-14. And what we can see also is that this sapropel was corresponded also to a time of high productivity. We can see that with the barium flux to the sediment, and we can also look at the redox conditions in the sediment with various proxies. Here, what is plotted is only the vanadium to aluminum ratio. Vanadium is a redox sensitive trace element that traps immediately when you have suboxic and anoxic conditions. So you can see spikes corresponding to this sapropel that is more or less in phase with the heart, the core of the African humid period. What is also very clear on that high-resolution graph is that the sapropel 1 was interrupted. You have two phases. Was interrupted in the middle, and this interruption that is not seen, in fact, in the flux of the Nile River is more or less corresponding to 8.2 thousand years before the present. So it's more or less corresponding to the phase that was identified decades ago by Françoise Gasse in Lake Abbé, for example. So what is also important with the study of sapropels, and this is a great tool because we can look at that in sediments, as in Mediterranean sediment, we can have a complete stratigraphy of sapropels and see that African humid periods with an S, with a plural, has been quite frequent in the past, in the deep past, because we know that sapropels were occurred since the Miocene. This is well known in Paléoclimatologie. This is just a few information that are summarizing, in fact, this fact. We observe that there is a cyclic deposition of sapropel, and the cyclicity that we see in the stratigraphy of deep sea sediments and also in sediments that have been uplifted, that are very old, that have been uplifted on land. This is, for example, from a quarry in Greece. You can see sapropels as dark bands. It's even exploited for the organic carbon, for the lignite. This is the Pliocene of Ptolemais. And we can see that also in the stratigraphy of deep sea sediment core. This is a core with, where we see the dark bands corresponding to the sapropel. And we know that this cyclicity, when we date the sediments, is corresponding to a cyclicity of 22,000 years, which is corresponding more or less to the precession of the equinoxes. So this is a summary graph for the last 2,050,000 years, where I summarize, in fact, the glacial, interglacial cycle over the time period, with the modern time period, the last glacial maximum with a much decreased sea level at that time. You can see the different glacial cycles, and at the same time, I put it here, I numbered, in fact, the different sapropels, S1, S2, S3, and so forth, S5 corresponding to the last interglacial. And we can see that they correspond, the timing of these sapropels in the stratigraphy correspond more or less to maxima of the insolation of the northern hemisphere at 65 north, but everywhere in the northern hemisphere. So clearly there is a link, a causal link between the insolation and the orbital insolation and the sapropel occurrence, and thus of the deposition of sapropel and the African humid periods as a whole, and the last one that occurred since the beginning of the Holocene. So obviously, the insolation had a role. This is a graphic that is summarizing all the forcings, of the climate forcings that occurred over the Holocene. And what we see, I mean, on that graph are a few curves. The first one, which is here, is the insolation linked to the orbital changes that are calculated by astronomers. The insolation at 60 north in summer, and we can see that it's expressed in watts per square meter, so we can see a large drop. This is half of the sine wave of 22,000 years, so in fact you have the maximum corresponding to 11, now we are in a minimum. So we have half of the sinusoid, so at the beginning of the Holocene, the insolation was maximal, and we observe a regular drop over the entire Holocene. At the same time, this is the contrary in the southern hemisphere, but we don't, we are not interested in that for the work of today. And of course, when we deal with the evolution of climate over such a long time scale, we have to care about other forcings. And for example, the solar activity has been studied with different tools. For example, the carbon-14 in tree rings. We can also work on that with the beryllium-10 in ice cores. And we can see some variability, but the variability is not exhibiting a long-term trend. It's more or less showing millennial structures. Some of them may or may not correspond, in fact, to climatic changes, but clearly this variability is at high frequency. It's also important to care about what was, at that time, over that time period, the greenhouse effect. And this is surveyed with the methane and the CO2 concentration mainly in the bubbles of ice core. So these are graphs summarizing, in fact, the time evolution of the CO2 and the methane in ice core. And you can see that there are trends, but the amplitude, for example, of the CO2 here is only 20 ppm. 20 ppm is not large in terms of forcing, in terms of climate forcing. As a whole, it represents a global forcing of less than 0.5 watts per square meter. So it's not very large in terms of forcing, even if the curve looks impressive. It can be compared, in fact, with much larger local, regional changes of the insolation that are tens of watts per square meters. For high frequency changes, it's also important to care about the volcanic eruptions, but they would add high frequency changes on top of the long-term evolution. Obviously, when we want to compare what is gathered from paleoceanographic work, reconstruction from different types of sediment, it's important to compare with the time evolution of climate that is simulated with models. And the models, numerical models, so this is just a cartoonesque picture of what is a numerical model representing mathematically the climate and the transfer of energy, matter such as water in the climate system, and it is constantly perturbed by known forcings and either seasonal or long-term changes. And the climate models, at the forefront of the science nowadays are using models that are coupled between ocean changes and atmospheric changes, and also they include the ice sheets sometimes. Here, this is a graph that I borrowed partly from Bill Rudiman from Lamont, and at that time, this is just for the convention, but there was no vegetation on that. I should update this because we will speak today quite a lot, not me, but mainly Martin Clausen with the modeling about the vegetation, the importance of the role of the vegetation on land. But clearly the ingredients are here. You have to couple the whole entire Earth system. So it is quite complex. The only tool to do that are models. And in models, the good thing is that you can inject to them one by one or collectively all the forcings that are known to occur over this time period. And very early in the field of numerical modeling of climate, the mid-Holocene climate has been studied by doing a steady state, more or less, experiment with climate models. And these were compared, these simulations, taking into account especially the change of the insolation over the last 10,000 years, were compared between different groups and summarized. So this is a summary graph that I took from the work by Pascal Braconneau, who summarized, in fact, this effort with many ocean atmosphere models in the frame of the PEMIP project. And this is a map, in fact, showing the anomaly of the temperature corresponding to the mid-Holocene, so mainly driven by this insolation change with different models and average. And what you can see is that, no surprise, because of this increase of the insolation in the northern hemisphere, most of the northern hemisphere was warmer. These are temperatures, but more. And we can also zoom at the northern part of Africa, and we can see that there was a warming all over the Sahara, for example, and Europe, and the Mediterranean. The other thing that is very robust and comparable in the different modeling experiment is also a large change of the hydrological cycle. This is a summary from the same work of compiling and comparing the different simulation. This is for the summer precipitation. We can see that the anomaly is, in that case, the convention are blue for higher precipitation. We can see that there was a much higher precipitation here. So the anomaly is, in fact, corresponding to a northward shift in the models, in all the models of the intertropical rain belt, what is called the intertropical convergence zone, ITCZ, at about 6,000 years before the present in the simulation. And we will see that this is corresponding more or less to what we see in the data. And there will be, of course, more complex issues that will be discussed on more recent modeling, but this is more or less to set the scene. It's clear that this long-time evolution of the insolation, it cannot be responsible, cannot be taken responsible for the 8.2 kiloyear event. And we know from quite large literature since about 15 years that, in fact, this 8.2 kiloyear event is probably, this is more or less the consensus now in the community, is linked, in fact, to a catastrophic release of the residual Laurentide ice sheet that was sitting on top of Canada. This is just a picture that is taken from the work of Barber et al. In 1999, where they identified the comparison between the timing of the abrupt drainage of this residual Laurentide ice sheet at the beginning of the Holocene that was located on top of Canada. And on the south, there were also very large, huge proglacial lakes, such as the Lake Agassiz and the Lake Ojibwe. And suddenly, at about between 8,500 and 8.2, there was a catastrophic collapse of the entire ice sheet through the Strait of Hudson up to the Sea of Labrador, the Labrador Sea. And obviously, this large amount of fresh water had an impact on the circulation. And it's very important to remember that this part of the world of the circulation, of the global overturning circulation, is very sensitive, in fact, to the input of the fresh water, because this is more or less the area where you have deep sea convections in different zones, but especially in the Labrador Sea. So this is a picture that is summarizing this modern picture. This is the simplified conveyor belt of Wally-Breuker, but this is basically the same thing with the global overturning circulation starting in the North Atlantic. So clearly, the freshwater input, very sudden, that corresponds, in fact, to the 8.2 kiloyear release from the residual ice sheet, was very important, dramatically important, and more or less affected this circulation that is bringing heat, in fact, from the southern hemisphere to the northern hemisphere in the Atlantic. Heat transport is also accompanying, in fact, this global overturning circulation. And there is quite a lot of information, literature on the impact of the fresh water that was released during that time period, mainly from the North Atlantic. And we see that, especially as a cooling, I mean, the timing is still an issue because different techniques are used in different archives, but clearly this cooling that corresponds to 8.2 kiloyear is seen in the Greenland ice core. This is a zoom of the Greenland ice core delta weighting stratigraphy, grip and north grip, and we can see a big drop that is corresponding, in fact, to a cooling in that case, and we can see similar cooling also in North Atlantic sea surface temperatures based on different types of organisms, mainly the foraminifera. It's also possible to see that to document in the same sediment with benthic foraminifera, those who are living at the bottom of the ocean, by measuring, in fact, carbon isotopes, it's possible also to document that, that this release, this outburst flood affected also the deep ventilation of the Labrador Sea. This is delta C13 stratigraphy, and there is a large drop of the C13 that is corresponding, in fact, to this 8.2 kiloyear event. So with the same type of models, it's possible, in fact, to study the impact of the 8.2 kiloyear event. This has been done by several teams. This is from the work of Legrande, from the GIS group at NASA in New York. The simulation, what they did is to release artificially in the model fresh water that is corresponding more or less to the flux from the residual Laurentide ice sheet. And obviously, this is an anomaly map that is corresponding, in fact, to this transient simulation. And what you can see is that the color code here is in red. You have warming. It's mainly widespread in the southern hemisphere, but the major change, especially for the North Atlantic, was a large cooling that is not due directly to the effect of the meltwater and iceberg. It's linked to the impact of the fresh water on the density structure of the North Atlantic and the heat transport in the Atlantic. What we are interested in also is that it had an impact, a far-reaching impact elsewhere, everywhere on the planet, in fact. And we can see that, for example, in the Mediterranean, there was a cooling. We can see that there was a cooling in part of North Africa. So clearly, even if things were happening here, it had an impact, and we can see that in lake levels in North Africa. And we have seen that also in the sapropels. We see that in all sapropels from the Mediterranean. With the same simulation, it's possible also to look at what it did to the hydrological cycle. This is a similar map taken from the same simulation, same work by the same authors, showing, in fact, that this release, this 8.2 kiloyear meltwater event, altered the hydrological cycle. And basically, what is seen here is a shift southward of the ITCZ. I mean, here you have to be careful because the color code is exactly the opposite as the one used by Pascal Braconneau. Here, higher precipitation is in red, whereas it was the opposite for Pascal. But that's the main message for North Africa is that there is a drying for the entire part of North Africa. A large part of North Africa. And of course, all the details are subject to discussions, but still, and it has to be compared with other type of simulation, with other models to map things and to see what is robust or not robust. But clearly, this is quite logical. In fact, with these housing experiments in modeling, usually they exhibit a southward shift of the ITCZ. The other thing that I don't want to expand, because we have the expert here today, Martin Clausen. It's very important. I mean, some of the simulations that I showed were steady state of the climate with different forcings. Some others were transient situation with, for example, the housing experiment with the release from the Laurentide ice sheet. But also for the Holocene as a whole, it's important to remember that even if a forcing is gradual, the effect on climate may not be parallel or may not be linearly linked, in fact, to the forcing. And a beautiful example was given something like 15 years ago by the work by Martin Clausen, who used a model of simplified complexity for the Earth system and the climate by showing that even if the insolation forcing for the Holocene, I mean here the time is evolving from left to right. So there are two differences in all the coding. Sometimes the colors are not corresponding between one author and the other, and also usually modelers are showing the time evolution from left to right, and the Paléoclimatologists are doing the opposite. Usually I put an arrow just for the people to remember in which direction the evolution of time is. So this is a summary graph taken from the work that was published in 1999, where Martin was able, and his colleagues were able to show that even with a gradual insolation forcing, the temperature in the Sahara band region the change was more abrupt, and it was also true for the rainfall and even more for the vegetation cover that was impacted by the climate in the model. So clearly there is an acceleration, and we more or less refer this as the abrupt end of the African humid period, and this will be the subject of long discussion probably today, whether or not we see that or not in the data here and there, and whether or not the models are compatible with each other, and what is the actual control on this abruptness versus the gradual forcing. I stop here because it's not really my field, and Martin will do that in a much better way. And clearly what we need now is also information coming from record in order to compare with what we understand from the modeling. And we need records that are taken either from land, from the continent, or from the ocean nearby North Africa. What I show here is just a few on a Google map of North Africa. I show just a few sites, sites that I already mentioned, Lake Abbé, Lake Assal, Lake Turkana, and so forth, and other sites that will be discussed today. And obviously, the entire map is much more crowded with many other points that will be discussed today or are in the literature, but this is an interesting topic. So today we will hear more about Lake Yoa with Stefan Kröpelin, Lake Chad with Florence Sylvestre and colleagues from the CEREGE, and obviously there will be also interesting information that is coming from ocean sediments, marine sediments that were taken close in the vicinity of North Africa, for example, of Mauritania. Probably Peter Domenocal will spend some time in describing, in fact, the work and reviewing the work that has been performed in that area. Jessica Tierney will give us more about what she is doing with colleagues, and Peter especially on the Gulf of Aden sediments. I already mentioned the Nile and the output of the Nile and its impact in the Mediterranean. At the CEREGE in Aix-en-Provence, we are also working on sediments that were collected off the Nile. And on that picture, I also showed, in fact, a star for a core that is located off Morocco that we are looking at the CEREGE. And I will mention, in fact, a few of the preliminary results that we have been gathering so far. And obviously, in order to understand the correspondence and to see if we can really understand what went during the Holocene, we need a much more much more data cover on that map, both with sediments all around North Africa and also on the continent. But as you will see, it's quite difficult sometimes to get that information. And because the end of the African humid period is also a time when ancient societies were either collapsing or evolving. At that time, I put out a few pictures, nice pictures from the Tassili, from Egyptian history, and this wet phase of the early Holocene also impacted areas that are much beyond, in fact, North Africa. It affected also the Near East and went also affected the Indus Valley, clearly. So what we can see on this Google map is already that the vegetation gradient that is appearing really on just looking at the Earth as it is, with dry and rocky parts in the Sahara, and you have the rainforest here, and obviously this gradient is linked to the African monsoon. The African monsoon, I don't have time, in fact, to summarize what it is, but this is, we can see it as a seasonal migration of the ITCZ that is bringing, in fact, water from the Atlantic that rains on the equatorial part and tropical part of Africa, that brings the water seasonally, and then there is a reversal, a shift of the winds in this area during the winter with a very hot and dry Harmattan wind, and this is basically the ultimate control of the vegetation in Africa. So this is two maps that summarize, in fact, the vegetation distribution in North Africa, and we can see just by comparing, in fact, with what I've shown just before, the impact of the rainfall and the water availability that controls really the African vegetation. We can see that the vegetation between the rainforest, represented here in green, and the more or less desert and the semi-desert, the Sahel part of North Africa, we can see a zonal gradient that is more or less corresponding to this moisture availability changes. And we can see also the vegetation, to simplify the whole thing, by looking at the distribution of the different plants according to their different photosynthetic pathways. The most common plants that are using the C3 photosynthetic pathway that are highly concentrated, for example, in the rainforest, and the C4 plants that are actually adapted, in fact, to the dry and arid and warm climate. And the C4 pathway is actually an adaptation, in fact, to the lack of water. And we can look at this by studying different proxies, isotopic proxies, or even organic compounds. We can do that, for example, by looking at the N-alkanes that are coming from leaf waxes. This is a nice picture that I borrowed from Isla Castañeda, representing what are leaf waxes. I like this, with engraving on a leaf. And this leaf are sun-blasted by the winds, and the N-alkanes are transported with the terrigenous dust. And it's even possible, in fact, to go further into the details by looking at the relative amounts of the different chain length in a chromatogram, in what we look in sediments or in aerosols or in continental marine sediments, and to look at the different distributions. This is a graph taken from a recent review and work on this field, and this is just a triangle diagram showing that by looking, for example, at the ratio between C31 and C29, you can distinguish between different type of plants, the dry ones and the woody one. And some authors even use, in fact, this C31, C29 ratio in atmospheric dust collected at different locations around Africa, and they show that there is a nice latitudinal evolution that is corresponding, in fact, to the percentage of C4 plants calculated with isotopic measurements of C13 that are completely independent. But clearly, there is a latitudinal evolution. The same type of work has been done in surface sediments in the southern part of Africa, and with a gradient of vegetation that is more or less corresponding to what we see in the north. You have an evolution of the abundance of the C29 and C31 N-alkanes, in that case, sediments. And as I said, we started, in fact, to work on a new record, a new deep sea sediment core that was collected off Morocco. And what we did in that case, for the moment, it's a collaboration with Sylvia Nav, and it was being performed by Frauke Rostek. What we see here is the stratigraphy for the last 500,000 years, with glacial, interglacial cycles that are documented by looking at the sea surface temperatures based on alkenones, a compound that are synthesized by algae, by crocodilophorates in the ocean. So it's possible to look at swings of more than 5 degrees Celsius over the last 500 years. So 500,000 years, we can see 5 glacial cycles. That's the last interglacial. And what we can see in the same course, in the same samples, are fluctuation of the N-alkane, the C31 to C29 N-alkane ratio that are more or less corresponding. So there is a quite nice match between the two. Obviously, I mean, we need to figure out what is linked to the vegetation changes and the transport, but this is ongoing work, and we may add other proxies as well. And it's possible to zoom at the part of the last glaciation that will be the subject of the discussion today. This is just the zoom of the stratigraphy for the last 20,000, starting from the last glacial maximum. And in the temperature that are reconstructed with alkenones, we can see very clearly the last glacial maximum, the Henrich cooling, the Alrod-Böhling warm phase, the Younger Dryas that is very prominent in that core, and the very sharp increase of temperature of more than 5 degrees, corresponding, in fact, to 11,500, 12,000 years before the present. And we can see also the time evolution of the N-alkanes. And of course, everything is preliminary work, preliminary time scale based on a few C14 ages and the delta 18 stratigraphy. What we need is to have a more densely covered stratigraphy with carbon-14. This will be probably one of the first core that we will date with our new instrument that was delivered only a month ago at the CEREGE, new accelerator dedicated to measurement of carbon-14, and we hope to have a much better chronology. So as a final comment, I know that I'm already too far in the discussion, but I would like also, because it will be important for the discussion that we have today about whether or not this transition is abrupt or not. Is this one abrupt? Abrupt has to be calculated in terms of gradient of the temperature or the humidity versus time. And of course, you need to be good with the Paléoclimatic information, but also with the timing of the event. And obviously, most of the information that we gather in this field is based on carbon-14. Not all. Sometimes it's possible to look at speleothems dated directly with uranium thorium, but most of the information that we will see today has been dated with carbon-14. And carbon-14, this is a slide that is summarizing what is, the principles of radiocarbon dating. The radiocarbon dating is based on fundamental assumptions. And because carbon-14 dating is actually the only dating tool that is based on the decay of one single isotope, we are not normalizing it to the ingrowth of the radiogenic nitrogen. So because of this, there is a fundamental flaw, in fact, in the carbon-14 dating. We need, in fact, to calibrate. This is this is a panel showing, in fact, the decrease of the radiocarbon in different samples, actually corresponding to the end of the African humid period. Woods from the Egyptian history that were dated by Libby in the 50s, and at that time, Libby did not realize that there was this fundamental flow that because of the time evolution of the production of carbon-14 in the atmosphere, the carbon-14 equation of time based on the measurement of carbon-14, the residual carbon-14 in the sample has to be corrected for the fluctuation of the initial production of carbon-14. So we do that, since the time of Libby, we do that by calibrating, by using a calibration of carbon-14 that is updated more or less every 3 to 5 years. And this is just two graphs as a final comment that will fuel the discussion, two graphs that I extracted from the last publication that we have released as the ANCAL group. This is the work by Reimer et al. 2013. This is the ANCAL 13 calibration, and I extracted, in fact, the two important graphs corresponding, in fact, to the start of the African humid period and the end of the African humid period. And in that time period, everything is based on counting tree rings and dating them by carbon-14 and realizing that carbon-14 is not precise. It can be precise, but it's not accurate. For example, here, this is what is marked as a dashed line is the one-to-one line. In other words, where data should plot if carbon-14 was not only precise but accurate, and we can see that there is a shift of something like 2,000 years at that time period. And more important for the discussion of today, there are many wiggles on this calibration curve. This is time, this is the calendar age, this is the carbon-14 age. So basically when you measure a carbon-14, for example, corresponding to the beginning of the AHP, you can see at 10,000 years something, 10,000 years before the present in carbon-14, you can see that because of the wiggles, because of fluctuations of the production and also of the carbon cycle as a whole, we observe that there is a plateau. So there is when we convert to calendar ages, there is already a built-in uncertainty of several centuries, 3 centuries at that time period corresponding to the plateau of 10,000. Even, if you increase the precision of your carbon-14, you won't get more precision because of this calibration prime. And this happened also at some other periods. There is a plateau here at 9.6 and so forth. The end of the AHP is not as bad as the beginning in terms of getting at the timing right and precise in order to compare with different archives. But you can see that there are structures and depending on your luck, the calibration of one particular C14 age will end up with a very precise age if you are here, for example, and precise. And if you date, if you have a carbon-14 age that corresponds to this or to this, you will have a fundamental uncertainty on the calibrated age of several centuries. So clearly, when you are trying to calculate rates of climate change, you need to take that into account. And so I know that I'm over my time, but I would like to close, in fact, this talk by showing, again, a picture that was given to me by Françoise. In that case, it's from the Paleo Lake of Assi El Mejna in the Great Erg of Algeria, and with deposits of diatomites. And with this, I would like to thank you for listening. And of course, what I describe will be updated a lot and discussed during the whole workshop. Thank you very much.